So I've added a couple of new things offline as I was talking about these to other people. Because now I think I got it to work. And so I added the Control Z gate, and I think I also want to add the uh, CCCZ gate, which is basically need to double these, I guess. Right, so we've got like 8, and so that is the thing. Uh, and this is definitely not, whoa, definitely not a -1. So now we have, there we go. Okay, we can keep that. And so, just this is an easier one to add. But it also shows a really interesting case, which is that the the case where we run a control Z on a state where the target is in the one state and the control is in a superposition, so we get like we don't get entanglement. But in the case of running a control Z, then we do get entanglement. And so I want to take a look at the differences in here. And I also realized one interesting behavior of implementing implementing the 2-qubit gates generically. And this is that it turns out, so this is for 3 qubits, right? It turns out that what you get at the end, like, is a bit different than what you get when you implement a controlled operation in the old way, using like apply controlled gate. Because here I was implementing it using a really specific logic where I was just splitting the control qubit and then applying the gate at the target qubit. Whereas if your gate is specified by a matrix, then the way that I implemented the apply to control qubit gate, which is basically by creating branches for each of the base states that you get out of just the multiplication of the matrix, it means that the amplitude that we're putting at the node level, where was that? The nodes. Okay, there's a to do here still. Then I do these, blah blah blah. The amplitude. So this thing here, which I don't think I should call this amplitude, but maybe I should. I don't know. This is what you what with the controlled implementation, I was getting a part of it by assigning it like this. When I split the edges, I was doing it like that, based on the control qubit. But then, whatever happened in terms of modifying the control qubit was happening locally at the control qubit. And so, for example, the global phase was added in the control qubit. Now, the target qubit. Sorry. Now, in this implementation, that doesn't happen. The whole thing gets added at the edge level. The reason being that, yeah, well, I do the matrix multiplication, so I essentially kind of do it locally for that subsystem, but it's still at the subsystem level, not at the qubit level, right? Yeah. And so what this does is that the minus, I don't know if you can see it, is added here. I'm also playing with having a better visualization for this stuff, but it's complicated. But you see the minus is in here. I can just zoom in. The minus is in here, right? Because here it's a branch where you have the 1 1, and this is the so the 1 1 and the 0 1, where it's like, yeah. But I kind of like it because it emphasizes a bit more that that what's added, it's to some extent it's to some extent really to some extent really related to the whole branch and not just to that qubit, because yeah, I think the whole control notion is just so misleading. It's just a two qubit operation. We shouldn't call this control. That's the problem. The fact that it has this effect shouldn't kind of force us to do that. But anyway, so because then I was like, yeah, now these two nodes are equal. So because what I wanted to try to start doing today is implementing the merging of the branches. And so you would say, okay, so those two need to be merged because they are exactly the same, right? In a world where I would just use the apply control gate, these would have a -1 here. So I would have to first guess, are they equal by a global phase difference or not? Which I still will have to do, I think. So I won't be able to skip that, but it seemed to be more natural in terms of why the phase kickback needed to be. But now at the end of the day, that this is really also something you see here, right? Which is that when we merge these two nodes, like these amplitude will have to go somewhere. So now I have an issue of interpreting these, right? Because it's like it's got to go somewhere. I almost feel like this is got to go here. This amplitude is going to be assigned totally here, and this amplitude is going to be assigned totally here. And I'm not saying that will be the only way of doing things, right? Because you could also think about merging these and then calling it just like a plus state, and then this amplitude goes here and this amplitude goes here. But then you wouldn't be able to merge that easily. Somehow, intuitively, it feels like this is what you should be doing, merging these two nodes. Yeah. I hope the code is more readable. Anyway, I want to take a look at what happens if I apply a CCZ, though. Although, oh crap, yeah, well, I need to generalize that for this to happen. So probably, I think I will not attempt these now. I think I'll just go with edge merging first, because I need to apply an n-qubit gate. Like I want to have a general implementation of these, which is probably going to be the only one that stays there, which is just like it's just basically qubits, right? Like qubits, and these being an array, right? And then the gate matrix will be yeah. So this is definitely a to-do. Apply n-qubit gate or multi-qubit gate, because then then we'll create like different amounts of Q nodes and we'll just do like a nested for loop. That's gonna be nice. And then we're gonna create all the yeah, this can also go in a loop, and then the cleanup. So that should be easy. I wonder whether this still needs to be in a single special case, because it's a 1 qubit operation, so it's just multiplication, there's no edges involved. Where if there's 1 qubit, I would say, yeah, well, it sort of has 2 edges, right? Like it's like an edge where the gate is applied, and another edge where the gate is not applied, or no, I don't know actually if I can merge these two, but yeah, let's go ahead and so this is what you get, which is correct. Now we want to merge that. So we want, because this is not true, like true in the sense that like this does not generate entanglement, so we shouldn't have these red and green edges, and so we should just go and merge them. And so the algorithm that I had in mind is something along the lines of, because at the end of the day, there's multiple ways to do that, I assume, but I think they're all equivalent. Of course, that's something left to prove, but I would just go qubit by qubit and say, okay, so I've got this node, and I'm gonna iterate and take a look at all the other nodes of the same qubit and say, hey, are they equal or not? Are they equal by a like up to a global phase or not? If they are equal, then I should merge them. And I'm assuming that the same node cannot be part of more than one entangled edge. I think that is a reasonable thing to assume. That is why I think this might not need to be done. Even shared edge. What did I mean by this? I don't know. We'll have to polish. We'll have to polish that, I guess. But so I guess we can call the function, something like it's like an update of the system. To be honest, like it's not a minimization. It's not a. It's like maybe it's just cleanup, right? Cleanup merge or something like that. Merge branches. We'll just call it. Let's just go easy merge branches. Okay, I'll give it a system. Although I don't know if I should not give it. No, I should give it a system. Let's make it just like with the system, because I'm thinking whether you can think of doing just like giving it a set of branches. Maybe I should give it a set of branches, set of edges, and a set of hyper edges, and then say, hey, can you merge these branches? Maybe that would be more useful, because if I think of what it means to do maybe measurement or collapse some things, like maybe that can be the way to go. So instead of going qubit by qubit, I would just go branch by branch. So I would say, so it's a bit of a different approach. I would say it's edges, right? Edges, okay, hyper edges, but whatever. And so what we would do here is we just, I guess, for E in edges, edge equals edges E, right? So we're getting the edge. And now what do we do? So what do I do? So how can I get the, because edges, so okay, I should assume this is an array. No, then I should do it this. So I should assume that it's an array. So or at least, so edges is a list. Because then what I would do is for, how is that in Python? Python iterate wrench. I think it was something like for I and range 0 to length of edges, so that is right. I, and then I just take a look at, so this is H A edge B right, and of course length edge is -1. We don't want to overflow. But, and so I'm basically comparing every possible pair of edges and then checking whether I can merge them. Now, the problem will be if I merge them, like I still might do multiple passes to these, right? I might need to do multiple passes to these. But I think the merge should be easy because I know that between two branches it can just be that like if there's this node, that there's another node or there's not another node of qubit 1 in there. So there cannot be multiple nodes of qubit 1 in one branch. I'm assuming that, okay? The problem is I fear there can be if we think about not pure states, but maybe I should just ignore these all altogether and assume assume this it's all about pure states. So good. So what am I doing? So I'm having these edges, and then I guess I should have a counter for, or like kind of have new edges, right? New edges maybe, which is a least, and then I just have like a counter that tells me, that I need to actually check some of these edges. Like, and if a merge, if an edge doesn't have, if an edge doesn't have, or the other way around. So new edges, right? And what I will do is I probably have to just remove it from new edges and add a new edge in here somehow. Yeah, I guess. So this should iterate over new edges or final edges. Sort of in a way that, like I'm dealing with edge A. If edge A cannot be merged, then I'll just remove it from F edges. I don't know. I feel that's just too complicated. But anyway, let's just ignore these. I'm just getting too hooked up on the details. So how do we know? So what is the best way to do these here? It's like merge. Can we merge two edges? Right. So actually, what should I do? So what I should do is I should just basically give into edges, edge A and edge B. I should go through all the nodes, right? So how do I do that? How do I do that? So what if I say, again, I'm not going to be printing these, I'm not going to be printing these. Well, I can print this, yeah. But what I want to do is I want to do merge branches of system edges, right? So that's what I'm doing. Maybe that's the best first attempt. Let's just print edge A, print edge B, And there you go, right? Like, we're not merge branches. So give it a set of edges, merge edges. And what it does is it returns, so far it doesn't return anything. It'll probably just return a set of, I don't know if it should return a set of edges or it should give it the system and let it and just return the system. At least these probably follows the pattern of the rest of the functions. So system and system edges, and so this is system. Yeah. Indentation error where oh, I can actually keep printing can keep printing the it's outside of the function. How dare I? Oh, come on. No. What is this? So print edges. Well, it's okay, so it's not a. This is because this is not an array. It's just an entity set, probably. Whatever. So because I need to be able to get the next edge, right? So where am I? I'm so lost. Here. Hypergraph. Maybe I just get edges or something. Edges. Elements, blah blah blah. Get edges. Collapse edges. No. So add edges. Can I Python trade over a dictionary? Get next element or something like that. Can I do this? Yeah, exactly. Maybe that's just a better way to do that. So I just print edges. So it's just, in edges, right? And then next item. Oh no, sorry. Enumerate. Okay. Yeah. Okay. For I, V in. Key list. There's got to be a nicer way to do that. Key shift. Lambda. Yeah, or I should just like so this is edges E, right? If I do that, that just prints nothing. So if I do enumerate edges, and I do like, right, what do I have? Print I 0 to 3, okay, yeah. Yeah, okay, I guess I guess that's the idea. Keys equals, what is the function called? Just keys. So if I do keys, okay, that's not the entity set. It's an entity set, that's why. It's an entity set. Maybe I should just go the easy way and say HA equals none, HB equals none, and so what I do is I just go through the edges and I say, well, the first I do is if HA is equals none, then I do HA equals edges E, else HB equals edges E. So I'm just saying, you know, either field A or field B. And then, yeah, and so basically what I say now is if HA doesn't equal none and HB doesn't equal none, then we, you know, do what we gotta do, and at the end set them to null, and at the end set, because I guess what we're gonna do is we're comparing. So and at the end, so you want to iterate over. So you first get. Oh man, I'm so fucking stupid. I'm just so stupid. I just should nest the thing. HA, just like retarded. I'm really retarded. HA equals edges. Oh god. E, right, and then I say for E in edges. HB edges E, and of course I have to assume now that if you know, edge A UID is different than HB UID, then we do what we gotta do, you know, else we just forget. And that's it, really. So print edge A, edge B. So Q1, 2222, yeah, exactly. Exactly. Now, what I also want to do is I want to ignore. Okay, this is something that I got to do in terms of edges, right? So I want to keep it those which are not. So not edges, but like I should do basically get just the entanglement edges. Entanglement edges. What be entanglement edges, and then say, which is basically just get entanglement edges as a function. Yeah. And now actually this returns finally. Yeah, I'm sorry, I'm just dumb. I'm just dumb. System. So we go to system. So this is one thing to do, right? Then I can give it any kind of edges and still assume it's a least. So what I do basically here is edges equals system edges, and I just say, well, for E in edges, edge equals edges E, and then I say like, so here I say result is an empty list, and I say if, so if E, so how to say in Python, string starts with Q or something like this, starts with true. Okay, so that actually exists. Hey, CPU, what's wrong? If E starts with Q, starts with ID, right? Then result append edge. Return result. So get entanglement edges. That is, why is it like liking so much? Am I running something funky or? It's lagging so much suddenly. I should just go here and run these. And I should never just run these. It's not defined, get entanglement. Edges is not defined. Why is it so slow? Okay, so I hope these will actually work because it's probably been like 5 or 6 hours. I kept this in pause as I got distracted with something else, and I just had to just go and yeah, came back to this, and I just realized that I had forgotten to start recording, and I did change some things in here. So let me see. So I'm working on the merge edges, and I realized that. So what I'm doing is I get entanglement edges, and then I kind of realized that I'm not getting the memberships that I want, and I'm really confused. So if I print out, if I go through the nodes of each edge, and I'm just taking a look at the entanglement edges, and I just go through these, for example, ID7, I print membership, print membership. It just prints the ID6, which is basically this edge, the entanglement edge. Sorry, ID7. 691. Oh yeah, sorry, the edges. And then I say ID10 belongs to, which is this node, belongs to ID9, but it doesn't say that it belongs to Q1. And that's what I want to know. I want to know to which qubit edges it belongs. And I just don't understand how is this thing stored? Like, if I'm iterating through the edges, like, what am I doing wrong? It seems to be, it's being drawn correctly, but like, it's like, really? Okay, so what if instead of just elements, let's just say I'll do system nodes. Okay, so I'm just going through the nodes, whatever. ID22. It seems something's not well cleaned up. ID22. What? What if I just print? So, what if I just I'll just do these, and I just print. I don't want to print this. Yeah, I don't want to print system. I want to print system nodes. Oh, come on. Really? Oh. Nodes. No, nodes. Yeah, whatever. So, what if we do really go through these? And we say in system nodes, and we print. Oh yeah, that is definitely a weird thing to do, probably. Print system nodes EL membership entities not object membership memberships. Why? Oh, it doesn't show that up. I mean, that is really confusing. So first of all, why do I have so many? Okay, no, so I just have 4 nodes, but they just don't show. Why is that? Yeah, no, I'm adding it to the edges, right? Whenever I do the operations, let's do one thing. So let's just, for example, let's assume we are operating on, we're just doing Hotmart, or let's initialize the system and see what happens. Okay, so kidding me. So that shows no memberships, but they're there. That's funny. So how is this whole? Oh God, I'm stupid. I know why. Because I'm never adding it properly. Oh, I'm just I'm doing these, and I shouldn't do it like these. Oh, I get it. So, uh, what I should always do here is I should say create node. So I should say node create node, right? State vector initial state, then node excited. This is node initial. Create node excited state. Oh, so I have my edge in here. Okay, I get it. So I need to give it a system. Okay, keep it edge. So I need to give it I need to do everything at the system level. Everything system, because those things just create nodes otherwise, and they shouldn't return these. So or not. No, 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 no. Let's keep those functions like we had them. Okay. So what the should do is it's not like that. Okay. I should just have create edge. I should just have create edge, which returns an entity set that is empty with amplitude. Voltage break, I just call it none. Keep it edge. And this doesn't exist anymore. Keep it create qubit edge, create node. Exactly. And so what from state vector does is create qubit edge, and then it does node initial. As I create node with initial state. And so what we're doing here is we're doing system add edge, right? hypergraphs, hypergraph module, add edge. So add edge. Do I have add edges or something? It doesn't matter. Come on, add edge. Q0 system add edge Q1. So this is where I was failing. Okay, so it somehow rendered well, but and now system node and node to edge. Right, I think there's something like this somewhere else used in my code, and then there's node and there's the edge. So node initial to Q0. So how do I deal with these? The edge to edge one. Okay, and I gotta do another. We'll just call this node 1, node 2. So this is node 1, Q0. I will call it node 0 just to be consistent with the qubit numbering. Okay, so now this should work. Zero's not defined. Where is this node? No, noted. Can this just work? Oh, node 0. Node 0. It's just slow. It's not really responsive. I don't know why. What's wrong now? Non-type. Okay. So we cannot give it a non. Come on, it's still not printing this? System from state vector. So just doing from state vector creates qubit edge, creates node, hypergraph, add edge, add node to edge. So first of all, let's see if actually, yeah, well, that draws it correctly. Why is it not printing? So if I just do it like this here. So nodes, memberships. Oh, there you go. Okay. So now it works. Somehow here so if I call merge edges, So wait a second, there's something I don't understand. Why is it that this works? So this works, but now I'm printing nothing, but I'm calling merge edges, and there's a print in here. So what is it doing? Edges. Oh yeah, it doesn't have any more edges now. That's why it's get a ton of edges. Okay, cool. So let's just do a Hotmart, and let's just do a Control X. Why I don't get these? Like okay, so maybe it's because I'm not adding these nodes. I'm cloning them, but I'm not adding them to the node edges, right? So what I'm doing, so this is Q0 node. Okay, yeah. So I'm just when cloning, I'm not cloning the actual memberships. That's what's not cloning. Whereas if I would just say, just as an experiment, if I would just say Q node memberships equals memberships, I'll probably have to do my own clone method, I think, just to make sure I have more control over this kind of stuff. Choose your own memberships, yeah, like parents. Okay. So I guess I have to add it. I just have to add. Oh God. Oh, but look at this. I'm adding. Oh, but that's not working. Of course that's not working because that's not an actual edge. That's not an actual edge. Keep it 0, keep it 1. Ah. Q0 edge equals system edges. Well, or just like that. I think that is what's happening. So this is the edge that I have to add stuff to. So I'm not adding it to the proper. That was a good catch. That was a good catch, definitely. I need to add it to the right qubits. Otherwise, how was that working anyway. So I'm adding the stuff where it needs to be now. And then when we apply gates, we clone, and that is wrong as well. This is the edge. This is the edge. How would how would that work? I mean, how is that working at all? I'm so lost. Cube 0 is not defined where? Of course it's defined. Ah, it's not defined. There you go. But it's still not working. So we just apply Hadamard gate. And I want to print all the memberships. And that works. That works well. So if I'm just applying like one gate, then that's all cool. When I apply a CX gate, then that doesn't happen anymore. Why? It's almost like they lose. So 37 belongs to edge 36. Exactly. It's just it looks like it's gone. Add node to edge P and Q to system edges Q0, Q1. Maybe I missed a case where Q1 node. Oh yeah, definitely the Q. Where are these things used? Oh no, those are nodes that are then just removed. Why do I clone them? So they're used just for these. Where else is these used? Q0 nodes, Q0 nodes. So I don't really need to clone these. To be honest. So this is Q0. This is Q1. Then I can get rid of these. So I'm not doing any funky extra work. You got that, and then I'm doing these, and then I'm creating a new edge. Right? I'm adding the edge to the system. I'm creating a node and a node. Okay, initial static status state. Yeah, those are the zeros and the ones and whatnot. Add node to edge. But I'm adding it. Why? I don't get it. I really don't get it. Why aren't these things added to the... Why is the membership lost? It's not lost here. Add node to edge. Nevertheless, it's just drawing the thing correctly. Oh, I don't get it. I don't get it. Clean up original nodes. Q nodes. Yeah. Here. So, this thing exists, right? Like, if I do these, like, yeah, Q0. Damn it. It's a damn edge. If I flip the order, does this, oh, you gotta be kidding me. But why? So now it's showing add node to edge. What does add node to edge do? So add node to edge. Yeah, okay, so it could be the UID, so that was correct before. Self edges, graph. But what's it doing? So add node to edge. So what it does if edge blah blah if is instance of blah blah if no blah 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 blah. So what it does is self edge add node. Yes, if not is instance of not envy node else no properties. Self. So if the node is already in the nodes, then you just add it to the edge. If the node is so add nodes and add in edges, but it doesn't. Memberships. Restricted nodes. Memberships. Update. It doesn't update the memberships though. It's funny, right? I mean, or just if you just take a look at the entities and let's take a look at the add code. Add. So that's add element. Add element does. Oh yeah, okay. So that's entity to item memberships. So adds an element to this item. Memberships. Remove element, add element. It just should work. Like, but it seems like add node to edge, add node to edge. I guess so the qubit 0, qubit 1 should actually work. But if I don't do these, then they'll show up anyway. That's weird. Like, do I have to? Is empty. I don't understand that. This should all work. Ah. It seems like if I add it seems to work, but the memberships are not updated or something. But that's not. System add node to edge. I'm adding the P node, which is just created here, to qubit 0 and to qubit 1. And then to the edges. So if I go again back to hypergraphs and I go to these, right, all this does is if node is in self nodes, it adds these to the edge. Okay, so if I go to entities, and add, it does add elements, right? That's what this does. It just that's for all, it does add element. And add element, well, that's these, right? So, and these actually add element. Self-reference, blah, blah, blah. Okay, maybe this is the case. There's something weird happening here. So it's already an element, so only the properties will be updated. I don't need in checklets. If item belongs to an element or a descendant of an element, then the existing descendant becomes an element and properties are updated. So I'm adding element, so self is the edge, and so I'm saying memberships. Checkles, I don't know what that is. But okay, but it's like checkles, these item memberships. So it looks like a global thing when there's if the item. If the item's UID does not appear in complete registry, then it is added as something new. So the memberships. Okay, so you're in both cases you're adding that. But maybe this is the case where it must be hashable. So if if item is instance of entity, we do these. Okay, but that's something new. I really don't get it. That should work, but I don't know why. Add node to edge. I mean, return self. Maybe. Yeah, I don't know. I think I have to stop here, to be honest. It seems like the memberships are not there. But there should be. And it's funny because if I'm replacing. Wait a second, maybe it's because the edge is something new. No, but I'm adding the edge to the system here. And so if I add this element to this edge, what is the difference between an entity and an entity set anyway? I'm using entities for nodes and entity sets for, but maybe that's the problem. So this has the elements and entity set. The entity set was class created to distinguish entities satisfying the bipartite condition. Oh, elements that are elements of the same entity set may not contain each other. As elements, the elements and children of an entity set generate a specific partition of a. Maybe that's the problem. What about replacing all these entity set stuff with just entity? Maybe then it just works. Maybe that enforces this bipartition thing. Okay, and because these are entity sets, maybe that's the reason. I'll probably I'll probably want to read that a bit more in detail, but where is it in the code? I cannot find it. Okay, maybe now, by any miracle, it just works. Yeah, wait a second. Or not. I don't think so. I don't think so. Maybe I didn't run everything. So I want these two to still be here. And so I want to run again everything. So I want to run the helping functions and this guy. No, and it doesn't work. Oh god. I had hope that it will work. But there's something funky with these. It seems like the order is actually it actually matters. It just seems like it's not adding these ones. I don't know why. And I thought maybe that had to do with the fact of entity sets and not entities, but it's doesn't do the case. I don't know. I'll look into this a bit more